All right, hello again. What we're going to do is continue moving on our unit about polynomials, and we're going to start matching polynomial equations with their graphs. And we can always use graphing calculators to show this stuff, or we can use algebra. I'm going to show you the algebraic ways because I like that better. I figure if you can perform more advanced algebra without the use of a calculator, then the using of the calculator becomes so much more helpful. So let's go with the general algebra first, and then we'll get back into later units about how to use the graphing calculator for stuff like this. So anyway, the goal is to understand, first of all, that all of these polynomials that we work with have a graphic representation, right? They make a picture. And what we're going to do is put stuff in function notation and then see which graphs belong to that equation. And there are a few ways to do this. And so what I'm going to do is look at each of the equations in function notation and then give you a couple of ways to interpret that to match those equations with one of the following graphs. So I hand drew these graphs, but they're kind of close. They kind of represent what the pictures actually look like. And so what we're going to do is investigate which one's which. All right. So these are the pictures that we're looking to match with each of these equations. So we start with the first equation. Now this is where some stuff can hopefully become a lot easier. So the first equation is f of x is equal to 5x cubed minus 6x plus 2. I'm going to show you two different ways to decide which of these graphs matches that equation. The first way is using ordered pairs, using an xy table. Okay? If we use an xy table, we can then start to figure out, well, which one's which. So what we're going to do is very similar to the previous lesson on evaluating polynomial functions. You pick your value for x, plug it into the equation, and see what you would get back for y. So for example, I'm going to use x equals 0. Why would I use that? Because it's so easy to work with. Because look at this equation. If x were equal to 0, what would happen? We would have 5 times 0 to the third power minus 6 times 0 and then plus 2. What's going to happen there? A whole lot of easy calculation, right? The calculation becomes quite simple. 0 to the third power is 0. 5 times 0 is 0. Minus 6 times 0 is 0. What's going to be left? Positive 2. So we have the ordered pair 0, 2. So right now what we know is that we have an ordered pair of 0, 2, right? So what we can then do is look at the graphs that we have and see which graph crosses through the ordered pair 0, 2. All right, so we look at the first graph in A, 0, 2 is right here. This graph crosses through it. So A is a possible graph. Look at graph in B. The ordered pair 0, 2 is right here. The graph of B crosses through 0, 2 as well. So it could be A and it could be B. Could it be C? Well, remember the ordered pair we just found is 0, 2. No, this graph in C does not pass through 0, 2, so it cannot be C. And it's the same story with graph D. It cannot be graph D. So right now, on this one ordered pair, we have discovered that it's either graph A or graph B. All we need to do is find out another ordered pair. So let's do that. If we pick our value of x, we can choose x to be 1, and then we can use substitution. Right? 5 times 1 to the third power, and then minus 6 times 1, and then plus 2. Right? So we can start crunching numbers. Now it's just like in the previous lesson, we now have order of operations and we can perform some stuff. 1 to the third power is 1. So we're looking at 5 times 1. 6 times 1 is 6, and then plus 2. 5 times 1 is 5, so we have 5 minus 6 plus 2. Therefore, it would give us negative 1 plus 2, which is 1. So now we have another ordered pair at 1, 1. And if you recall, where did we leave off? We had one of two graphs that this function could represent. It's either going through 0, 2. So it's going through 0, 2, so it's either graph A or graph B. Right? But this graph is also passing through the order pair 1, 1. So now we take a look. Which graph crosses through 1, 1? So we have in graph A 1, 1. Well, it's awfully close. So, I hand drew this, so we don't know. And what about B 1, 1? Well, again, it's awfully close. I hand drew it. So what's going to make the difference, right? What if we use 2 for our x? Remember, we're choosing between these two graphs. If we're going to choose 2 for our x, this graph goes up, this graph clearly goes down. So choosing 2 for x would be a much greater explanation of which graph belongs to this function. So we're going to do just that. We're going to find what's going to happen if x was 2. Okay, so we plug in our values. 5 times 2 to the third power, then minus 6 times 2, and then plus 2. We're going to evaluate that. Okay, we're going to see what order pair we have if x was 2. So we have 5 times 2 to the third power is 8, right? So 5 times 8, then minus 12, and then plus 2. So 5 times 8 is 40. 40 minus 12 plus 2. So that gives us 28 plus 2, which is 30. All right, that's easy. So if we have the order pair at 2, 30, we can now clearly see which graph this belongs to. Okay? So we can look at our differences between graph A and graph B. But what was the ordered pair we just found? 2, 30. So in this graph, 2, 30 would be way more reasonable. In this graph, 2, 30 is not reasonable at all. So clearly the correct graph is graph A. So that's how we can always do this. Always do this. And that's the last I'm going to show you for this method of matching graphs, because the next method I'm going to show you has to do with what we have discovered previously in my notes called the guaranteed pass notes. If you remember the notes for the guaranteed pass notes, we worked with parent functions. Do you remember parent functions? So we have to remember parent functions. And if you recall from previous lessons, the parent function is the most simplified version of the operation occurring. So if we look at this particular equation, the operation that's occurring to the variable is x to the third power. So the parent function happens to be y equals x to the third power. Now, if you recall from the guaranteed pass notes, if we were to graph this particular equation, what we would find is the following. We would have a shape that looks something like this. Okay? So if we had y equals x to the third power, 1, 1, 0, 0, negative 1, negative 1, right? 2, 8, negative 2, negative 8. We have a graph that looks something like this. That means it is starting low and ending high. Okay, so starting low and ending high. Because remember, we read left to right. Starting low, ending high. Now, which of the following graphs on this list follows that model? Only one graph starts low and ends high. That is graph A. If you look at graph B, it starts low and ends low. If you look at graph C, it starts high and ends high. If you look at graph D, it starts high and ends low. So we can use parent functions to actually determine which of these graphs match with the others. So if we look again at the first equation, f of x is 5x to the third power minus 6x plus 2. The parent function is y equals x to the third power. And we recall from from our previous lesson on the guaranteed pass notes, okay, the graphs of algebra. This is what y equals x to the third power looks like, okay? And we can use that same method with the rest of the equations. So let's do that, okay? Let's do that. So for the second equation, we had g of x is equal to negative 2x squared minus 6x plus 2. Okay, so that was the second equation now. And I'm going to, again, use parent functions. Can you use a table of values? Absolutely. You would have 0, 2 for an ordered pair, and you would find out what's going to be for 1. You can use the same thing. You can always use table of values. But I want to look at parent functions again because it's such an important concept for graphing. So if we look at the parent function of this equation, we would find that we have the most simplified version of the exponent of the operation is x squared. So the parent function is y equals x squared. But I want you to notice something. If you remember that a, the lead coefficient, is negative. So we're actually looking at y equals negative x squared. All right, so that's kind of the parent function we're looking for. This graph is going to be represented by something that looks like y equals negative x squared. So why did I label those notes the guaranteed pass notes? Because if you understood them then, this is going to make a whole lot of sense. If you didn't understand them then, this is not going to make a whole lot of sense, and hopefully I'm helping. So if you remember, y equals x to the second power is a graph that opens up, right? It's a parabola that opens up, and y equals negative x squared is a graph that opens down, right? So if you remember that from translations, right? So the unit on translations, we're going to find a graph that opens down. And so this then starts low and ends low. Okay, so the graph that we're looking for starts low and ends low. So we go to the graph that we're dealing with. Which graph fits that description? Which graph starts low and ends low? Graph B, right? So we can clearly see that graph B is the graph that matches equation number 2. Right? So, well, funny irony, right? So you pattern seekers are saying, well, 1 was A, 2 was B. I wonder if that means 3C. I actually don't know because I haven't figured that out yet. So we're going to move on to equation number 3. We have h of x is equal to negative 2x to the third power minus 3x squared plus 3x minus 2. And again, you can use a table of values. And again, I'm going to say, well, I'm not going to. I'm going to use the parent function. So the parent function of this crazy equation, the most simplified version of the operation, is y equals x to the third power. Okay, that's the most simplified version of this equation. However, the lead coefficient is negative. So we're looking at y equals negative x to the third power. But again, this is in the notes, the guaranteed pass notes. It's all there. I'm just reiterating some stuff. So if we were to graph y equals negative x to the third power, what would we find? We would find a graph that looks like this. A point at 0, 0, a point at negative 1, 1, 1, negative 1. We would have a graph that looks just like this. Okay, so that is y equals negative x to the third power. That's the parent function of this. This is just a crazy, mixed up, modified version of a graph that looks like this. And what's happening in this graph, it is starting high and ending low. Well, that's weird, right? It starts high and ends low. So which graph fits that description? So if we look at our 4 graphs, starts low, ends high, starts low, ends low, starts high, ends high, starts high, ends low. So graph D is the match for equation number 3. Now take a look at that equation number 3. Remember the parent function. The parent function had this characteristic, right? Negative x to the third power. But when you add all this other stuff in there to the parent function, it's going to bend it a couple times, right? And that we'll get more into that later, but that's just what's called end behavior and how that matches. So we know that for equation 3, it is graph D. That is the match. Okay? So now we're going to, obviously, process of elimination is equation number 4, but still, let's take a look at parent function. So in equation number 4, we have j of x is equal to 3x squared minus 2. And what we're going to do is investigate, again, parent functions. So the parent function is the most simplified version of the operation that's occurring. And in this case, it's y equals x to the second power. Okay, so what is that going to look like? This is positive, so this is positive. And if you recall, y equals x to the second power is a parabola opening up, which means it's going to start high and end high. All right, so we're going to come in high and we're going to come out high. Okay, so start high and high. And that's the parent function. So which of the following graphs models that? Clearly it's graph C, and that's how we would know, holy cow, the parent functions are awfully similar. It's just that we do a couple things to the equation that are a little bit different than the parent function, and it affects the graph of the parent function. Okay, shifts it a few ways, bends it a few ways, but the end behavior remains the same. So the matching graph for equation 4, of course, is graph C. And that is how we would be able to match equations with graphs. So a quick review. We can do one of two things. We could either make a table of values and start plugging in stuff and matching ordered pairs to where they exist, or we can understand end behaviors and parent functions. So I go back to the guaranteed pass notes. I hope you had fun. I did. I'm out.